Good afternoon, everybody. Now we are starting with magnetism, electrostatics and electrodynamics. It's over actually. Now we are starting with magnetism. So first of all, we will be in this chapter 32, we'll be studying what is magnetic field, the definition of magnetic field, how do you get the magnetic field? Okay, all these things, or the effect of magnetic field, these things we'll be studying in this particular chapter. So let's start off. So electrostatic interactions, symbolically, you've seen that one electric charge interacts with another electric charge via what is called the electric field. Or electric field was the concept that was able to explain the action at a distance. So two charges which were not touching each other were still influencing each other. So we presume that there is something called an electric field. One charge sets up an electric field at the location of the second charge. Therefore, the second charge experiences a force equal to charge into the electric field at that point. So this is how electrostatic interactions were explained. Now, similarly, can you have an analogous interaction for magnetism? So if there is something like that, what would you have written? You might have written a magnetic charge and another magnetic charge will interact via what is called the magnetic field. Next comes the question, is there something called a magnetic charge? So quite obviously the answer is no, there's nothing called a magnetic charge. But then whenever you talk about magnetism, you've all heard of magnetic poles. You've heard of something called a north pole, you've heard of something called a south pole. You know that a north pole of a magnet is one which when suspended freely will point in the direction of the geographic north. That is, it turns towards the north pole of the earth. Hence the name north pole for that part of the magnet. Similarly, you have something called a south pole also. And you know why the north pole of your magnet is turning towards the geographic north. Please, I'm using the word. The north pole of your magnet is turning towards the geographic north. That is simply because closer to the geographic north, you have something called the magnetic north. Please remember, the earth itself is a magnet. The earth is a magnet. And towards the north pole of the earth, you have your magnetic south pole and vice versa. So that's the reason why your magnet tends to align itself towards the magnetic south or the geographic north. Okay, and the best example of a magnetic source is going to be a bar magnet. Then I gave you the example of earth also. And in all these discussions, we find that there is a south pole, there is a north pole. Both these always come together. You cannot separate a north pole and a south pole. You cannot separate a north pole and a south pole. If you take a magnet, cut it into two also, there is a new north pole and a south pole coming into picture. Therefore, you can never create what is called magnetic monopole. You cannot create what is called magnetic monopole. Magnetic monopoles do not exist. And this is quite different from what you've seen in the case of electrostatics. In electrostatics, on the other hand, you have a positive charge, you have a negative charge, and these two can be separate. They can exist in isolation. But that is not true for magnetic poles. They always come in a pair. Okay. Now let's, so you can't use the word magnetic pole, meaning like in the case of electric charge, you cannot write a magnetic pole interacts with another magnetic pole via a magnetic field. You cannot write that simply because magnetic monopoles don't exist. Okay, so you know that just as in the case of electric field, you can always represent magnetic field strength also in terms of magnetic field lines. Okay, and the only difference between electric field lines and magnetic field lines is that magnetic field lines are always closed loops, whereas electric field lines start on a positive charge and end on a negative charge, whereas here they form closed loops. Like for example, here you see the picture, there is a bar magnet given to you. There is a bar magnet with the north and the south pole, and you look at the magnetic field lines. You're finding that each of the magnetic field line is forming a closed loop. A closed loop, and you can see that it emerges from the north and then closes in from the south, but then doesn't stop at the south. It actually forms a closed loop. Okay, and if you look at the earth here, there is this earth picture also given to you. That is just to show you what happens if you have a bar magnet or a compass. What will happen? You will find that it is pointing, the north of these bar magnets will always point towards the north pole of the earth, which is where you have your magnetic south. Okay, and again you can draw the same things that you've studied in electric field also. Wherever the electric field lines are closer, there the magnetic field is larger. And if you draw a tangent to a magnetic field at a point, that gives you the direction of the magnetic field. Those ideas you can borrow. Only difference is magnetic field lines form closed loop. They emerge from the north and enter from the south. Okay, so now you know that you cannot write something called a magnetic dipole, a monopole, and a magnetic monopole interacting via a magnetic field. That you cannot. But instead, magnetic interactions can be represented. Magnetic interactions can be represented in this particular fashion. A moving electric charge. Please remember, in electrostatics, we talked about charges which are at rest, okay, or at most moving slowly. But here we can talk about a charge also as a source of magnetic field, okay, and a charge, a moving charge can also can get affected by a magnetic field. So instead of writing a magnetic monopole, you will be writing moving electric charge. So two moving electric charges can interact with each other via the magnetic field that each of them sets up at the location of the other. Okay, whereas in electrostatics, you had static charges interacting with each other via the electric field. Here, moving electric charges can interact with each other via the magnetic field. And you know what is moving charge. In chapter number 29, you've seen that moving charge is simply your current. Okay, or you will conclude that electric current can be a source of a magnetic field. It can set up a magnetic field. And another electric current, which is in the location of that magnetic field, will experience a force from the first electric current. Or you talk about the interaction between two current carrying conductors. You know that parallel current carrying conductors, anti-parallel current carrying conductors. In one case, there is an attraction. In another case, there is a repulsion. Now, these attractions and repulsions are due to magnetic forces. Okay. Now, how do you know that there is a magnetism associated with a current? So for that, look at this picture here. Okay, look at this picture here, 32.03. You can see that here is a wire carrying a current in the upward direction. And you look at the magnetic field. You're finding that the magnetic field forms closed loop. And look at the direction of the magnetic field. The magnetic field loop is going to be like this. North is this. This is the direction. So this is the direction of the magnetic field. Okay, and you look at the next picture. In the next picture, you're shown a current. The current is in the opposite direction. But here, if I have to represent the magnetic field forming closed loops, you find that the magnetic field is in the opposite direction. So the direction is always the north pole. Okay, that you take as the direction. Okay, now, what is the analogy for electrostatics? The analogy for electrostatic was, if you had a charge, a static charge, then there is an electric field at all points around this charge. This is the analogy. Okay. And if this is a positive charge, if it's a negative charge, the electric field lines would have gone inside. So this was the analogy. But in magnetism, the analogy is a current carrying conductor is behaving like a charge, but then the magnetic field lines are forming closed loops. And then another thing that you've seen in electrostatic is that if you take a charge Q0 and put it in an electric field E, it will experience a force Fe equal to Q0 into E. Now I am for the first time putting this E subscript because now we have to talk about magnetism also. So we have to make a distinction between electrostatic force and magnetostatic forces. Okay, therefore we are putting that E there. So magnetic force is equal to the charge placed in the electric field into the field. Or quite obviously, you can see that the electrostatic force will be parallel to the electric field if Q0 is positive, or it will be anti-parallel if Q0 is negative. Okay, but Do you expect to see something similar in the case of magnetism? Meaning, in the case of magnetism, what would be the relationship between the magnetic field and the corresponding force? The magnetic field and the force, what would be the relationship? Can you write an equation like what you have written above that green line? Okay, so that's the next thing we are going to see. Okay, or in summary, whatever we have discussed till now can be just summarized and written in the form of 3 sentences. What are those 3 sentences? There is no magnetic field associated with static charges. There is only electric field associated with static charges. Therefore, there is no magnetic force also. Magnetic field is associated only with moving charges or currents. The second point is a charge moving relative to the source of magnetic field. A charge moving relative to the source of a magnetic field can be a probe to detect and measure the field. If I have a current carrying conductor, and I'll call it 1, if this sets up a magnetic field B here, and I'll call it B1. Okay, now if I put another current carrying conductor here, if I put another current carrying conductor I2 here, then the force that I2 will experience, the force that I2 will experience will help me in measuring B1. Or this moving charge or the current carrying conductor I2 can be a probe for measuring the field set up by the first current. I hope this point is clear. Basically, what we are trying to tell you is that a current carrying conductor or a moving charge can be used to measure an unknown field. We are talking of magnetic field, so that means the magnetic field has to be measured. Okay, so how do you measure it? By using a moving charge or a current. And if that is in the location of the magnetic field that you want to measure, then using the force experienced by that moving charge or the current, you can measure the magnetic field. So a current carrying conductor or a moving charge can be a probe. A probe is always, you know what's a probe, right? You must have heard of, there is a commission set up to probe the crime. So probing means finding. So here you can actually probe or measure the magnetic field. Then another thing is, a moving charge is also a moving charge or a current is also a source of magnetic field. It can be a source of magnetic field. That's what we have seen here. I1 is a source of magnetic field B1. And I2, when you place there, experiences the force. By studying this force, I can find out what is B1. So that means moving charge or current can be producing magnetic field. They can be source of magnetic field. Similarly, moving charge or current can also be used to measure magnetic field. That is how the two of them interact with each other. Now, what are you going to study in chapter number 32? In 32, you're going to see the effect of magnetic field. You're going to see the effect of magnetic field. What is the force it creates? Magnetic force. You're going to study in chapter number 32. You don't bother about the source. You don't bother about who created that magnetic field. I know that there's a magnetic field. So what is happening to a charge there? So that's what you're going to study in chapter number 32. When you go to 33, you're going to study the source of the magnetic field, how a moving charge or a current becomes a source of a magnetic field. So that's the relationship between chapter 32 and 33. Any doubts? Okay, so now we start off with the simplest of situations. Now we are going to study. We're going to probe magnetic field. Right now, I only know the word magnetic field. I don't know what is a magnitude. I don't know what is the direction. I'm interested in finding that. Okay, and how do I find that? I'm not going to use straight away a current for measuring that. I'm going to use a moving charge. I'll take a very simple situation. The simplest of situation is a region where there is a magnetic field. I want to probe it. I'm going to take a small charge which is moving and put it there. And then we have seen that we have to study the force that it will experience. By studying that force, we are going to now define what is the magnetic field in that region. Okay, so what I'm going to now explain is going to be a series of observations in a thought experiment. Please remember, this is not an experiment that you can really do in a real life because the forces are going to be very small. So you cannot actually do this experiment. You cannot perform this experiment, but then you can actually do a thought experiment. So what is this thought experiment? Let us see. Are you following what I'm saying, guys?
Ma'am, you are not audible.
Good. I just wanted to know whether you people are listening. I purposely just tried moving my lips to know whether anybody is there at all. Okay, so somebody is there. Thank you for that. Okay, so let's consider a region of space. So sometimes I have to do what you are doing to me, right? Tit for tat. Okay, so now consider a region of space where there is a magnetic field. And also ensure that there is no electrostatic field, because electric field can also apply its own force and all that. So we don't want that effect. So we want a region where there is no electrostatic field, but you know that there is a magnetic field. And then you're also going to somehow, it's a thought experiment, okay? So you're also going to ensure that other effects like gravitational forces also don't exist there. You're going to do it in a chamber where the gravitational force is not there, electrostatic force is not there, only a magnetic field is there. You're going to take a charge q. You're going to take a charge q, which is obviously moving with a velocity v in this region. And you're going to move that charge, or you're going to vary the charge, and you're going to move the charge in various ways, and then see how the force is going to change, how the magnetic force is going to change. And by observing this magnetic force, we are going to define the magnetic field. Okay. So let me just start off with a picture. So let's say that this is your charge. Let's assume it's a positive charge. And let's say this charge is moving with a velocity v in this direction. Okay. And what do I see? I find that this charge is experiencing a force. And let's say I have an instrument for measuring the force. I'm able to measure a force, and I'm finding that there is a force, and this force is perpendicular. The force that we're seeing is perpendicular to the velocity direction. Okay. Then next thing that you do is keep the speed the same. Keep the speed the same. Only change the direction of the velocity. Keep the speed the same. Only keep changing the direction of the velocity. When you change the direction of the velocity also, every time you're finding that the magnetic force is perpendicular to the velocity. Okay. But then what is happening is that for a certain direction of velocity, which we are going to call as the reference direction, for this direction of velocity, we find that the force is zero. The force FB is zero. Magnetic force is zero. And you're going to keep doing this so that, 180 degrees is covered. You're going to keep doing this. Okay. And you're also finding that with respect to this reference direction, if you take another direction, which is perpendicular to the reference direction, if you take a direction perpendicular to the reference direction, you're finding that the force is a maximum. The magnetic force is a maximum. I hope you're understanding this. For all directions of velocity, you're finding that FB is going to be perpendicular to the velocity. So that's the first point. The second thing is keep the speed the same and keep changing the direction. You find that for a certain direction of velocity, the magnetic force is zero. And for a direction which is exactly perpendicular, you're finding that the magnetic force is a maximum. Okay. So that means you're finding that the force is going to not only depend on the force is perpendicular to the velocity, but then the magnitude of the force depends on the direction. For some direction it is zero, for some other direction it is maximum. And for any other direction that you are considering, for any other direction that you are considering, like what I've shown here, for any other direction, you're finding that the magnetic force is directly proportional to V sine phi. It is directly proportional to V sine phi. It is proportional to V, the speed, all right. It is also proportional to sine phi, where phi is the direction, the angle that the V vector makes with the reference direction. Are all these points clear, guys?
Yes, miss.
Right. Okay, now let us go ahead and see the rest of the observations. Now, when you reverse the direction of, when you're going to reverse the direction of the charge, you're finding that the force direction gets reversed. The force direction is getting reversed. So that means not only the velocity magnitude, the direction also matters. And then when you're reversing it also, you're saying that FB direction is getting reversed. And then another thing you're noticing is that FB is also found to be directly proportional to the magnitude of velocity. Yes. If you keep changing the speed, you're finding that FB keeps increasing. There is a direct relationship between the magnitude and the force. And you're finding that the magnetic force is zero when the velocity is zero. Or in other words, all of these we can club together and write that FB is proportional to V sine phi. Okay? And finally, you're finding that FB is directly proportional to the magnitude of the charge. If you do this experiment with a proton, you get a certain force. If you're going to do it with an alpha particle, the force is going to be different because the charge is different. Okay, so that means it's proportional to the magnitude of the charge. And similarly, it's found that FB direction is also related to the charge sign. If it's a positive charge that if you're doing the experiment with an electron, FB direction is something. If you're doing the same experiment with a proton, the FB direction is getting reversed. Or from all this, you are able to list some factors on which this is going to depend. So the first is FB is proportional to V sine phi. The second thing you're finding is that FB is perpendicular to the V direction. The third thing you're finding is that FB is going to be proportional to the magnitude of the charge. And fourthly, you're finding that FB direction depends on sign of charge. Okay, so now you're going to put together all these observations. You're going to put together all these observations and arrive at some equation. You're going to arrive at some equation, or you're going to not arrive at an equation. I will say now you're going to define magnetic field. When I say define magnetic field, there are two things. One is the direction of the magnetic field. Second thing is the magnitude of the magnetic field. So let's see how it is defined. So defining magnetic field based on the observations of this experiment. So the first is direction. How are you setting the direction of the magnetic field? Direction of the magnetic field is a direction of velocity for which the force was zero. You remember you called one velocity direction as the reference direction. So whenever the charge was moving in that direction, the force was zero. So that direction is taken as the direction of the magnetic field. Next, so now you fix the direction of the magnetic field. Next, you need the magnitude of the magnetic field. To get the magnitude of the magnetic field, you're going to take that perpendicular direction. You're going to take the perpendicular direction where the magnetic force was a maximum. Okay, now you're going to define the magnitude as FB max divided by QV. FB max is the maximum magnetic force. FB max divided by QV. We are putting a modulus for Q because we are talking of a magnitude. Or now we are going to define the magnitude of the magnetic force as QVB. We are going to define the maximum magnetic force magnitude as QVB, just the product of Q, V and B. So first we got the direction. Next we have got the magnitude of the maximum force. Maximum force we are going to take and then write it as QVB. And from this, we can't just leave it like this. we also need to take forces where the magnitude was not a maximum. Okay, so there what we are going to do is we are going to say FB is equal to QVB sine phi. QVB sine phi. FB max is QVB. For all other direction, it is QVB sine phi. Okay, when phi becomes equal to 90 degrees, you get this. So that means what you have written for FB max is contained in this more general equation. Okay, and additionally, you know that magnetic force is a vector, velocity is a vector, magnetic field is a vector. Therefore, you write it in a vector form as FB is equal to QV cross B. Okay, so this is how you define the direction of the magnetic field and a magnetic field magnitude. Now try to see whether this obeys all your observation. It will obey all your observation. You will find that the magnetic force is perpendicular to velocity. Whenever V and B are parallel or anti-parallel, you're going to see that FB is 0. Whenever V is perpendicular to B, then sine 90, you're going to see that FB is a maximum. And here you can see that whenever V becomes opposite in direction, FB has to become opposite in direction. Similarly, whenever the charge is going to, if you do the experiment with a positive charge, you get a certain FB. If you do it with a negative charge, you're going to get the opposite. If you're going to do it with a proton, you get a certain force. If you're going to do with an alpha particle, you're finding that the force is proportionally going to increase. Or you can see that all your experimental observations are obeyed by this particular equation. Okay, now you're seeing that there is a cross product involved. There is a cross product involved. Okay, so here magnetic field is a vector, and not only that, now you have to see that FB is perpendicular to the plane containing V and B. Till now we said FB is perpendicular to V, but then from this equation FB is perpendicular to the plane containing V and B. And please note FB direction, let us do it for a positive charge. FB is direction for a positive charge is given by V cross B, the right hand rule. Right hand rule. Look at this picture. I don't know whether if I show it here you will understand. Look at the picture there. It's a positive charge moving along V vector. Put your right hand so that your right hand base is sitting on the velocity vector. It is sitting on the velocity vector, and turn your fingers along the small angle towards the B vector. Turn your fingers, the right hand fingers, from the V position, turn your fingers along the small angle towards the B vector and look at the direction of the thumb. Thumb gives you the direction of the magnetic force. You can see that FB is perpendicular to the plane containing V and B. But please remember, always go for the small angle. Now, what if it's a negative charge? What if it's a negative charge? Certainly, you know that it will be in the opposite direction. Always use your right hand rule for a positive, assuming it's a positive charge, and then put the opposite sign if it's a negative charge. Any doubts?
No.
Okay, so let's see. Okay, so you can sum up whatever we have seen till now, that determining the magnetic field involves two measurements. One is the magnitude and the other is going to be the direction. Direction you're getting from the zero force direction, and magnitude you are getting from the maximum force direction. What is a unit? Now from this equation, F is equal to QV cross B. Okay, you can actually write your magnetic field in the simplest way as Newton by Coulomb meter per second. Coulomb is charge, meter per second is velocity. And you know that Coulomb per second is ampere. Therefore, you can write it as Newton per ampere meter. But both these together have another name, and that is Tesla. Okay, so the SI unit of magnetic field is Tesla. But then very often, you must have heard of a unit called Gauss. You must have heard of a unit called Gauss. What is Gauss? Gauss is a much smaller unit when compared to a Tesla. Okay, 10 to the power of -4 Tesla is 1 Gauss. 10 to the power of minus 4 Tesla is 1 Gauss. A Tesla is something that you create inside a lab using an electromagnet. You know that current is a source of magnetic field. So using large currents, you can produce a magnetic field which is close to Tesla. So Tesla is something that you're artificially creating inside a lab. What is this Gauss? 1 Gauss is a magnetic field associated with regions close to the surface of the Earth. Earth is a magnet we have seen. So if you look at the magnetic field close to the surface of the Earth, you'll find that the magnetic field is approximately 1 Gauss. Okay, that's how that 1 Gauss unit came. 1 Gauss is not an SI unit, but it is a popular unit. It is a popular unit. Okay. Now that you have understood what is a magnetic field and you have understood the relationship between magnetic force and magnetic field, now we need to see something. There is an observation that you have made. You have seen that FB is always perpendicular to the velocity. If FB is perpendicular to the velocity, it is certainly perpendicular to the displacement. If FB is perpendicular to the velocity of a body, of the charge particle, that means it is also perpendicular to the displacement of the charge particle. Okay, now think of it. There is a charge particle moving. You're seeing that FB is this. Then, what is the work done by this force? What is the work done by the force? You know, work done is F dot S. What is the angle? Angle is 90. You know that cos 90 is 0. Therefore, you can always assume that work done by magnetic force is 0. Work done by magnetic force is always 0 because it's perpendicular to the displacement. Now, so that means you can safely assume that magnetic force does no work on a charge particle that is moving. Magnetic force does no work on a charge particle that is moving. Now let's quickly go to work energy theorem. You know that work is also equal to change in kinetic energy. If work done is 0, then change in kinetic energy is 0. If work done is 0, then change in kinetic energy is also 0. So you come to this very important conclusion. Magnetic force cannot change the kinetic energy of a charge particle. Magnetic force cannot change the kinetic energy of a charge particle. Now, what is kinetic energy? Kinetic energy is half mv square. Okay, so you can also safely say that magnetic force cannot change the magnitude of the velocity. It can change direction. This means that it can change direction, but it cannot change the speed of a moving charge particle. Because it cannot change the speed of a moving charge particle, because the work done is 0, change in kinetic energy is 0, but it can change the direction. You know that if a particle is moving along the east and then moving along the north with the same speed, the kinetic energy has not changed. So that is what your magnetic field can do. Magnetic force can change the direction of a moving charge particle. It cannot change its speed. It cannot change its kinetic energy. Is it clear, guys?
Yes, sir.
Okay, so now quickly let's work out a problem. You are having a person sitting inside a room. Okay, you're seeing his head from above. Let's imagine that you're looking at the room from above. You're looking at the room from above. This is your room. Okay, and you're seeing it from above, from the ceiling. So what are you seeing? There is a uniform magnetic field B with magnitude 1.2 millitesla. And it is pointing vertically upward through the ceiling. It is pointing vertically upward through the ceiling. And please remember, any vector can be represented by an arrow. The tip of the arrow, if you see from front, will look like a dot. And the back of the arrow will look like a cross. Okay, therefore, any time you're going to see dots like this, that means you are actually seeing the magnetic field coming towards you. Okay, out of this plane. If on the other hand, I show this, that means I'm seeing the tail of the arrow, it is going inward. This notation you must remember. Okay, so now let's go to the problem. So you're seeing that the magnetic field is going out of the roof and it is uniform magnetic field. Why do I say it's a uniform magnetic field? When you drew electric fields, you were drawing the electric fields like this. But here you're sitting in front and looking like this. So you're only seeing the dots. This is a uniform magnetic field. I say uniform because the spacing of all these dots is uniform. Okay. Now the value of the magnetic field is 1.2 millitesla. A 5.3 mega electron volt proton. So Q is how much? Plus 1.6 into 10 to the power of minus 19 coulomb. A proton which is having an energy, it's having an energy of 5.3 mega electron volt. What is mega? 5.3 into 10 to the power of 6 electron volt. Now, do you know how to convert electron volt into joule? You studied this in mechanics. How do you convert electron volt? Electron volt is a unit of energy. How do you convert it into joules? Don't remember anything. 5.3 into 10 to the power of 6 into 1.6 into 10 to the power of minus 19. If you multiply, you will get joule. Multiply by the charge of a unit charge, then you get joule. Okay, next. I'm interested in the velocity because after all, I would be certainly interested in finding out what is FB. I know FB is equal to QV cross B. Okay. And for doing this problem, I need to know what is my, what happened? PowerPoint not responding. 1 second. I need, what happened? Close this, 1 second. Everything that I've done is gone. Okay, so let me just quickly write again. So what all did I write? I wrote Q is equal to 1.6 into 10 to the power of minus 19 coulomb. Then I wrote that the energy, kinetic energy, which is half mv square of the moving charge proton is equal to 5.3 into 10 to the power of 6 electron volt, which you know is equal to 5.3 into 10 to the power of 6 into 1.6 into 10 to the power of minus 19 joule. Okay, this is half mv square. I would be interested in if B equal to QB cross B. Okay, so I want my V. So what will be my V? V will be equal to 2 times 5.3 into 10 to the power of 6 into 1.6 into 10 to the power of minus 19. Okay, so this 2 I took there. M I have to come to the denominator. What is the mass of a proton? It is 1.67 into 10 to the power of minus 27 kg is given here. Okay. And then this is V square. So if I want V, I have to do under root. Okay. So we get the velocity to be equal to 3.2 into 10 to the power of 7 meter per second. That's the velocity of the charged particle. Okay, next what we do is, we'll keep it here. Or before that, let me see. Before that, so I got the velocity. So the energy of the charged particle was given to me. The proton was given to me. From the energy, we have now found the velocity. And how is this proton moving? The proton is moving horizontally from south to north. So that means before we start this problem, we have to fix up our east, west, north, and south. So this is north, this is your south. With respect to north, your right is going to be east. Okay, so you have your east and this is your west. So this is my proton. The proton, in which direction is moving? It is moving south to, it is moving south to north. It is moving south to north with a velocity v. And you found out the velocity v. Okay, now what is the force that is going to act on it is what you have to find out. What is the force that is going to act on it is what you have to find out. What is FB? FB is equal to QVB sine phi. What is sine phi? What will be phi? Remember, everything is happening inside the room. The charge particle is moving inside the room from south to north, whereas your magnetic field is this. So what is phi? Phi is the angle between the velocity and the magnetic field. So what is it? 90 degrees. 90 degrees. Phi equal to 90 degrees. Okay, so from here you will write FB is equal to QVB. Okay, so you can find out what is FB if you just substitute charge, velocity, and then magnetic field. So charge is 1.6 into 10 to the power of minus 19 into velocity is 3.2 into 10 to the power of 7. Then into magnetic field is 1.2 into 10 to the power of minus 3 Tesla because it is milli Tesla. Then we find the value of the force to be 6.1 into 10 to the power of minus 15 Newton. 6.1 into 10 to the power of minus 15 Newton. Okay, but then this is just the magnitude. How do we get the direction? You have to use your right hand rule. Put your hand, right hand on the first vector. Which is the first vector?
Velocity.
Velocity vector. Put your right hand on the first vector and then turn it towards the second vector. Second vector is B, and then look at the direction of your thumb. Okay, when you do that, you are getting that the thumb direction is this. Thumb direction is this, which is east. Which is east. So you have to say that this is towards the east. Now, if you look at this value, 10 to the power of minus 15 Newton, it's very, very small. So that means the magnetic force on a tiny charge is going to be very small. That is because the charge itself is very small. Okay, so then should we really bother with these kind of things is the next question. You have to bother is the answer, because you can see what the author says. He says the force may be very small, but then if you try to see what is the acceleration, this force is acting on a proton. Okay, so the force is equal to mass. The effect of the force is going to be an acceleration. So F is equal to m into a. F is equal to m into a. If you try to see what is the acceleration, you will find that the acceleration is around 10 to the power of 12 meter per second square. Because mass is very small, okay, even though the force, magnetic force is very small, F is equal to m into a. When you substitute and get a will be very large. So in that sense, the acceleration will be large. Okay, so you cannot ignore this magnetic force. And this magnetic force has got a lot of applications, which we will be seeing one after the other in the coming sections, coming class actually. Okay. In fact, this chapter is my favorite chapter. Of all the chapters in the book, I like this chapter the best because it's a lot of applications. Okay. So now, what we next do will be So till now, we kept assuming that electric field is not there. Electric field is zero in that region of space. There is only magnetic field, we said. What if there is an electric field and a magnetic field? So there will be a force on the charge corresponding to electric field, and there will be another force on the charge corresponding to magnetic field. Now you may ask a question, but all the time we thought that electric field will be there only if the charge is at rest. No. Electric field will be there even if the charge is moving. Only thing is we kept on talking of electrostatics all these days because we wanted to avoid the magnetism effects. Okay, so if you have a moving charge, there is going to be a magnetic field and an electric field. Both effects can be there on it, or both can actually affect the moving charge, or the net force acting is going to be the sum of the electrostatic force and the magnetic force. The first force is QE, the next one is QV, V cross B. And the sum of these two forces is called the Lorentz force. Okay, now this Lorentz force has got a lot of applications, which you will be seeing one after the other. The first application is going to be velocity selector. See, what happens is, you may be needing some experiment where, you have to play with ions of a certain, or let us say you want a stream of electrons to perform some experiment. So when these electrons are coming out, you'll see that they're going to have a wide range of velocities. Those of you who have attended the lab session, yesterday there was a lab session, remember? Okay, in that lab session, which was the experiment that we discussed in physics yesterday? Anyone? Thermoelectric effect. And when we studied thermoelectric effect, do you remember the photoelectrons which were getting ejected from the cathode? I said they have a wide range of kinetic energy. So they will have a wide range of velocity. You remember that? Okay, so you have to think that is the most common thing that will be true for any charge particles which are getting ejected out of any ejector. You will have charge particles with a wide range of velocities or kinetic energy. But in certain situations, you want to separate out all those charge particles which are having a single velocity. You want to get rid of all other charge particles which are having velocities greater or less than what you want. Then you use what is called a velocity selector. Okay, let's see how a velocity selector will work. We'll see that in the next class. Any doubts?
No, ma'am.
Okay, great. Fine then, I will stop sharing. And please guys, start preparing for your test too. Just because it got postponed, don't think that it is not there. And is there a quiz or something now? How many quizzes are over? I'm forgetting.
2, ma'am.
2 are over. 2 are over. The third also is there now, no? I'm unable to remember. Anyway, please remember, for quizzes there will be no makeup will be given for quizzes. Last semester we just made a small exception for the first 3 quizzes. The reason was people had not got admitted. They were still getting admitted. Otherwise, for a quiz there is no makeup. Please don't miss your quizzes. And before I wind up, 1 more minute, I just want to tell you something. We find in the lab session, we have finished 7 experiments. 1 more week, we'll finish the 8th experiment. With this month, we want to finish off the labs so that you are free to prepare for the end semester examination next month. From next month, you should be seriously preparing for your end semester examination. Meanwhile, we find that in every batch, there is a group which is not attending class, which is not submitting also. Not attending class, not submitting records also. So far, they have all got zeros. We would like to give such people one last chance. No special classes will be taken for them, but there will be one opportunity given for them to submit. We'll give them 1 week time to submit 4 of the experiments if they have missed anything. Okay, and similarly, another week for submitting 4 of the other experiments if they have missed anything. Remember, this is just a small opportunity given. They will certainly not be given the marks that the first timers are getting. The first timer marks are varying between 18 to 24 out of 25. 18 is minimum we are given, up to 24. But these guys will get a minimum of about, say, 12 or so only. But if they want to escape getting 0, I want all such students to make use of this opportunity. This is the last opportunity. After that, don't come saying Corona, Kirana and all that. Corona doesn't stay for, because I also got it, I know it doesn't stay forever. Okay, so you couldn't have missed all the experiment because of Corona. So please make use of such an opportunity which is being extended to you. And this is normally not done. We are doing it only because of special circumstances. Make best use of that. Okay, that's it. You can leave now.